So in today's session, we will discuss about the different starting methods used in the case of a three-phase induction motors. Now you know that the three-phase induction motor is a self-starting motor. That means there is no separate mechanism required for starting the motor. It is already self-starting. Now, as per the working principle, that is when a three-phase AC supply is given to the stator winding, a rotating magnetic field will be generated. Now, when the rotor conductors are placed in this magnetic field, an EMF will be induced. A current will flow through the rotor circuit, and the interaction between the rotating magnetic field and the current carrying conductor will generate a torque, and the motor will rotate. Okay, now why do we need this starting methods? That is what we have to find. Okay, now let us analyze this three-phase induction motor. At the time of starting, means the speed of the rotor NR is equal to 0, right? And what about the slip? Slip will be 1. So this is a starting condition. That is when the rotor is at the standstill condition. Now, from the equivalent circuit, we know that the impedance or the resistance which is connected in the rotor circuit is given by R2 dash plus R2 dash into 1 minus S by S, right? So this is the equation of the impedance in the rotor circuit. So what will happen when the slip is 1? This value will be very small, or it will be approximately equal to 0. That means on the rotor side, the resistance will be almost 0, which means the current will be very high, because current is inversely proportional to the resistance. So what happens is, at the time of starting, due to this very low resistance, a very high current will flow if we are providing the full line voltage to the stator winding. So that means if the stator winding of the three-phase induction motor is given the full line voltage at the time of starting, a very high current will flow. So this current has to be controlled, because there are several reasons for that. Okay, now let's analyze this. Why we have to control this current, or what is the effect of this initial high starting current? Now, there are mainly two methods for starting a three-phase induction motor. So now we understood that there should be some method while starting the induction motor in order to control the initial flow of high current. So the first method is, it is called full voltage starting, and the second one is reduced voltage starting. Okay, so in the full load starting method, we usually call it as direct online starting, or DOL. In this method, the full supply voltage will be applied to the three-phase induction motor. That is why we call it as direct online starting. Okay. Now which is the next method? The reduced voltage starting method. And in this method, there are three types. First is the autotransformer starting. Okay. Second one is the star delta starting. And the third one is the stator resistor or reactor starting. Okay, but here we will be analyzing only two methods, that is the DOL starting and the auto transformer starting. Okay, we will study in detail these two methods. Now this reduced voltage starting method has got the advantage that initially when the motor is started, the current which is drawn from the supply line, that is the initial high current, can be controlled, but the torque which is proportional to the supply voltage, it will be reduced. Okay, so that is one of the problems while using this reduced voltage starting, that is the current can be reduced, but then along with the current, the starting torque will also get reduced. Okay, now we will move on to the first method, which I call direct online starting. So this is a high voltage starting method. Now in this method, the stator of the three-phase induction motor is connected directly to the three-phase supply line. Now since the impedance of the motor at standstill condition, that is since the impedance at the rotor side is very small, a very high current will flow, and we can say that low power factor starting current of 5 to 7 times full load current. See, starting current is about 5 to 7 times the full load current. Okay, now such very high current, if it is flowing, this current, large current, it will flow only for a very short duration. So it will not affect the induction. Suppose if we are using a squirrel cage induction motor, this high starting current will not affect this motor that much because it is only for a very short duration. Why? Because you know the squirrel cage induction motor, physically has got a rugged structure, and it can withstand this high starting current. Then what is the problem? There is problem. This high starting current will affect the other equipments which are connected in the supply line. So it is not only the induction motor that is connected to the 3 supply AC, there are other equipments also connected. So what happens is, due to this high starting current, there will be some voltage drop in the supply lines, and this will cause undesirable dip in the supply line voltage. So this is the issue. So due to this high starting current, maybe squirrel cage induction motor will not be having any problem, but the other equipments can be affected. See, this can be noticed, that is during very peak load time. Suppose when you are switching on the refrigerator, and then inside the refrigerator we have the induction motor. So when at the instant of starting, that is at the instant when this induction motor gets started, you can see that there will be some flickering of this bulb. Okay, so you know that the problem, I hope you understood what is that problem. That is, there is a voltage drop in the supply lines. Okay, so that is creating this undesirable dip in the supply. Okay, so that has to be controlled. Okay, now in the case of direct online starting methods, we will try to derive the relation between the starting torque, full load torque, starting current, and full load current. We will see how they are related. Okay, now let's analyze this. Now you know the rotor input is the same as a stator input, and the power is given by omega into T. Okay, here the speed is a synchronous speed. So I can write the rotor input as this 2 pi ns, I will take it as a constant. So I can write rotor input equal to K into T. So from where did I get this equation? That is P is equal to T omega, where omega is equal to 2 pi ns. N is a synchronous speed in RPS. That is why there is no 60 there. Otherwise we will put it as 2 pi ns by 60. Okay, now this relation also we have learned, that is rotor copper loss is given by slip into rotor input. Now here instead of this rotor input, I will substitute K into T. Okay, S is S into KT. Now what about the rotor copper loss? It is a 3-phase system. So the copper loss is 3 into I2 dash the whole squared into R2 dash, where I2 dash is a current flowing in the rotor winding referred to the stator side. R2 dash is a rotor resistance referred to the stator side. Now from this we can find a relation for the torque. Okay, this is a constant, so this can be ignored, and this also can be taken as a constant, and this 3 is also a constant. So finally we will get the relation torque is proportional to, this is the equation, that is torque is proportional to I2 dash the whole squared by S, or slip. And this I2 dash, that is the current flowing through the rotor winding, it is proportional to the stator current I1, right? So we can write it is proportional to I1 the whole square divided by S. Okay, because I2 dash is proportional to I1. Okay, now we can slightly modify this relation, that is if IST is the starting current. So this is our intention is to reduce the starting current, right? So let's take IST as a starting current and starting torque as TST for a better understanding. Then we can, the same thing can be applied to this particular equation. We will get the starting torque TST is proportional to IST the whole square. Here you can see there is no slip because I have taken slip is equal to 1. Why? Because this is the starting torque. So only for the starting torque, in the equation slip will be taken as 1. Okay. Now let us analyze the full load current, that is when the motor is completely in the loaded condition and it is full load is applied. At that condition we will take the current as IF. IF is a full load current, and slip we will take it as SF. So please note that when the motor is running under full load condition, the slip is not equal to 1. I have taken the slip as equal to SF. Okay. Now the same equation we will apply here also. So we will get the full load torque is proportional to full load current the whole squared by SF. Okay, so we got equation number 3. So this is equation number 2 for the starting torque, and equation 3 represents the full load torque. Now we will divide 2 by 3. Okay, so we will get starting torque by full load torque is equal to starting current by full load current the whole squared into slip. So this is the equation. Okay, now we will just try to compare this, or we will just give some sample values and see how it will be affected. Okay, now again you know that this current starting time, what is the current in the three-phase induction motor? Starting time, it is something like the rotor circuit is having a very low impedance, so the current will be very high. So we can take that current as a short circuit current. That is, rotor circuit appears like to be short circuited. So that is why I have replaced IST by ISC here. See, ISC represents the short circuit current during the starting time. Okay, so this is the equation. Now just assume that initially when the motor is started, the starting current or the short circuit current is 5 times the full load current. So I am taking ISC is equal to 5 into IF. And also I am taking the slip as 40%. So S is equal to 0.4%, 0.04, because you know the value of the slip is between 2 and 5. Okay, 2 and 5%. So I'm taking it as 4%. So substituting these values, I put the short circuit current ISC is equal to 5 times the full load current, and the slip I put it as 0.04, and just to see what will be the torque, we will get the starting torque, and that is TST by TF is equal to 1, which means starting torque is same as a full load torque. Okay, the current is very high, but the starting torque will be same as a full load torque. So this is the analysis of the direct online starting method used in the case of three-phase induction motor, and this method you call it as high voltage starting method, and it can be used both in the case of three-phase squirrel cage induction motor as well as slip ring induction motor. So now here we can see that initially there will be a very high current, okay, and the torque, starting torque will be equal to the full load torque. Okay, now let's move on to the next method. Now this is one type of reduced voltage starting method. So as I told before, now here in this method we are not applying the full line voltage to the stator of the three-phase induction motor. That is, suppose if V is the full line voltage, we will not apply the full voltage V to the stator. We will apply a fraction of this, like a fraction X into V. It can be either 60% or 25% or 40% of the supply voltage. Okay, so reduced voltage is applied to the three-phase induction motor. Now, because the thing is that this condition will be maintained until the motor retains its speed. Initially, the motor rotor is at rest. That is why we are giving a reduced voltage. Once the rotor starts rotating and attains a sufficient speed, then we can apply the full line voltage to the stator winding. Okay, now we will see this arrangement. Now here you can see the auto transformer. So this is the auto transformer. This is the auto transformer. Here we are giving the three-phase supply. Now IST is a current which is drawn from the supply, and V1 is a full line voltage. Okay. Now this full line voltage is given to the winding of the auto transformer, and see the output of the auto transformer winding. It is starting from here. So there is some tapping here. See the voltage, it is not V1, it is X into V1, and this voltage is given to the winding of the stator, right? So the voltage across the stator winding is not V1, it is XV1. Okay, so what will be the current? Current will be X into ISC. Okay, similarly the other winding also we can see there is a tapping provided, and we are not giving the full line voltage, we are giving X into V1. And this tapping X can be 65% or 80% or 70% of the line voltage. So basically we are providing a reduced voltage to the stator winding of a three-phase induction motor using auto transformer. Okay, now here you can see the rotor also. Rotor is given here. Okay, now we will see this. So here we can, as I told you, we are not applying the full voltage V1, we are applying X into V1. Okay, that too at the time of starting, only at the time of starting using an auto transformer, we are applying a reduced voltage XV1, which will control the initial starting current. Now when the motor accelerates and attains its original speed or the rated speed, then this auto transformer can be disconnected, and then we will be applying the full line voltage, okay, full line voltage to the stator winding. Okay, Now just we will analyze this. See, after using this auto transformer starting method, what advantage is there we will see. So this is what I explained before. In the case by using this auto transformer, initially the current through the stator winding is not ISC, it is X into ISC. See, the current is reduced, right? So the current which is flowing through the stator winding of a three-phase induction motor during the starting time is now X into ISC, where X is less than 1. That means the current will be reduced. Okay. Now we can apply this condition, that is the output voltampere of the auto transformer must be equal to its input voltamperes. That is, we are neglecting the no load current of the auto transformer. Input VA is equal to output VA. What is input VA? Input voltage into current. Let's see what is the input voltage into current of the auto transformer. See the input is V1 and current can be taken as ISC, right? So that is what is written here. That is V1 into IST. What about the output? Output voltage is XV1 and this is the output current. So this is the output voltage. I can write it as VO. This is the output current and this is what is applied to the stator winding. So I am equating this equation. Then from this we will get the expression for IST. So what will be the starting current IST from this? What is IST? IST is a current which is drawn from the supply. Okay. ISC is the current which is flowing through the stator winding. So don't get confused. IST, here you can see the exact difference. So IST is the current which is drawn from the supply and ISC is the current which is flowing through the stator winding. So now let's derive an expression for the supply current. So from that we will get the supply current IST is equal to X squared into ISC from this particular relation. What is the meaning of that? In the case of a three-phase induction motor using auto transformer, we are applying a reduced voltage XV1 to the stator winding initially and the current through the stator winding will be X into ISC. But what about the supply current now? That is supply, from the supply only X squared into ISC will be drawn. That means the supply line current, that is the current drawn from the supply line, is reduced to X squared times the short circuit current. Okay, so that is a good thing, right? Okay, now let's just we will see what about the torque. So our initial objective is satisfied, that is the starting current is reduced both in the stator winding as well as the current that is drawn from the supply. But what about the torque? So the same equation we will apply. So here you see the starting torque by the full load torque is equal to the current. That is, what about the current? Here the current will be X into ISC the whole squared. You can see it here, this particular equation. So starting torque by full load torque is equal to X into ISC by IF the whole squared into SF squared, which means when compared to the direct online starting method, there is an additional X squared coming here. This X is less than 1, right? So that means the starting torque will be reduced. Okay, so by using an auto transformer, the starting current from the supply or from the mains, okay, IST, and the starting torque both are reduced to X squared times their corresponding values with direct online starting. Okay, so that is a conclusion. That is, when we compare this auto transformer starting with the direct online starting, we can see that the starting current from the supply as well as the starting torque is reduced to X squared times. Okay, so these are the two methods of starting three-phase induction motor, that is DOL, direct online starting, and auto transformer starting. This can be used in the case of both types of motor, that is squirrel cage as well as slip ring induction motor. Now just we will try to work out a problem to get a better understanding of this. Okay, so these equations you have to keep in mind, whatever equations, that is equation for starting torque, equation for maximum torque, full load torque, everything. Okay, now the question is the ratio of maximum torque to full load torque, that means Tm by Tf. Tm by Tf is given, that is the ratio of maximum torque to full load torque in a three-phase squirrel cage induction motor is given by 2.5. Okay, now the question is calculate the ratio of starting torque to full load torque for a direct online starting. Direct online starting, this is what you have to find. And what are the values which are given? The rotor resistance R2 is given. Then rotor standstill reactance X2 is also given. So R2 is 0.5 and X2 is 5. These values are given. Okay. So first let's write the equation for the starting torque. The starting torque is given by K into E2 squared R2 by R2 squared plus X2 squared. This equation already we have learned. Again, the equation for the maximum torque is K E2 squared by 2X2. This also we have learned. And this it is given in the question. Okay, so now substitute for the maximum torque here. So matter is K into E2 squared divided by 2.5 into 2 into X2. Okay, so we will get this expression. We will substitute for this X2 also. Okay, so we got this expression. Now again, we are supposed to find this ratio, that is starting torque by full load torque. Now starting torque equation already we know. We can substitute this particular first equation. At that by TF. TF is what? TF is also given, that is K into E2 squared. But so we are substituting the equation, that is TST and TF in this particular equation. From that we will get this expression. Okay, and now so R2 expression, R2 already we know the value of R2. Just a substitute for R2 as X 0.5. And when you substitute X2 also you know, that is X2 is also given, that is 5. So substituting the values, we will get the ratio of starting torque to full load torque as 0.49. So for doing this question, the only thing you have to do is you have to remember the equation of starting torque and maximum torque. All other expressions and values are given in this particular question. Okay. Now let's try to do one more problem. Determine a suitable autotransformer ratio. That is, we are supposed to find the ratio K for starting a three-phase induction motor with a line current not exceeding twice the full load current. Line current not exceeding twice the full load current. So that is a condition given. Okay. The short circuit current is 4 times the full load current. That is also given. So short circuit current is 4 times the full load current. So that is a relation. See, short circuit current is 4 times the full load current. Slip is given 2.5%, that is 0.025. Slip will always vary between 2 to 5% for a three-phase induction motor. Okay. Now here you are supposed to find the K, that is the transformation ratio, autotransformer ratio, and also the starting torque in terms of the full load current. Okay. Now let's see how to do this problem. Now the supply line, already I told, IST is equal to what? K squared into ISC. Right? Now it is given that the supply line current at start is equal to 2IF. Okay, that is IST. IST is equal to 2 into IF. And ISC is equal to 4 times IF. These two relations are given. So what is the relation? ISC, that is the current which is starting time, the current flowing through the stator winding is given as 4 into IF. Okay. And here another relation is given, the supply line current IST is equal to twice the full load current. So using that equations we will get this one. Okay. So substituting this, then we can find the value for K. K will come out as 1 by root 2, that is equal to 0.707. Okay. So this is how you can find the value of the transformation ratio. So these two equations are given. One is starting current IST is equal to twice IF, and ISC is equal to IST twice IF, and ISC is equal to 4. Using that equation you can find the expression for K. Okay, because this is the equation. You know that supply line current, instead of IST you can put it as K squared ISC. Here it will be K squared ISC. That is K squared ISC will be equal to twice IF. Okay. Now ISC, instead of ISC you put it as 4 into IF. That is how you solve this equation. Then how will you find the ratio starting torque to full load current? So this expression is for the starting torque to full load current, and using that we will find TST by TF is equal to this particular equation, K squared, because this is auto transformer, that is why this term K squared is coming. And we know the value of ISC, it is given 4 times IF. okay, and SF is also given, and finally we will get 20%. Okay, so that means starting torque is 20% of the full load torque in the case of using this type of auto transformer. Okay, so here which are the main equations? Main equations is this one, that is supply current is equal to K squared ISC, and then this particular equation. All other conditions are given in this question. Okay, so I hope you got an idea about this starting of three-phase induction motor.